Jenny Petit. I am an education coordinator for the Canadian Light Source. I am so happy to present the Science of Making Bannock video. This video will introduce you to summer students that have a science background, as well as it will contain some traditional knowledge. So the traditional knowledge that I bring to this video is learned from my extended family from the Wew'suwaka'pill First Nation in Anishinaabe culture. I also have teachings from my adoptive father from Opaskwayak Cree Nation, Northern Cree teachings as well. So that's where some of the information that will be included in this video comes from. First, I'd like to introduce our one summer student, Jessie Parenteau. Jessie is a member of the Métis Nation of Saskatchewan. He is also a recent graduate of the University of Saskatchewan College of Education. His major was in chemistry, and he has brought a lot of the chemistry portions to this video. Our other student is Julia Doucette-Garr. Julia is a Métis Dene from the English River First Nation. She is currently completing her Bachelor of Science degree at the University of Saskatchewan, and her major is in physics. She will be contributing a lot of the physics portion of this video. So we really wanted to try and create a little information about the background in our process that we did in making this video. Our teachings converged at a point where we had, even though we come from diverse backgrounds, we had similar knowledge about the four elements. And the four elements that I'm talking about are fire, water, air, and earth. So what we did is we started to brainstorm and think of all the history and what did all of our women face once they would have received these ration boxes, and what changes would have happened. So when we look at fire, we would have looked at over time they were cooking on fire. They may have started in log homes and would have learned how to use wood heat, like from a wood stove, and then that could have become a gas stove or an electric range like what we have today. So they would have evolved these recipes, these science experiments to adjust for a different type of heat and the thermodynamics. We also looked at water and where did the water come from? Where does the water go when it gets into the recipe, and how did they compensate for that? Because many of our relatives would have been gathering water from waterways and like sloughs, ponds at that time, snow in the winter time. So those water have many different elements in it and would create a different kind of recipe. Then from there, they would have went to well water, which again, now we have all these different elements from the earth that are in the water, and that would have impacted the bannock, that would have impacted the recipe. And so they would have been adjusting and understanding what all of these elements, when you add them into an experiment, happens, what it does, and how to adjust for that, so that our bannock could still be light and fluffy and wonderful to eat and comfort us during hard times. So these are some of the processes that I encourage the teachers to use with your students. It was certainly fun to do with our students at the Canadian Light Source, and to really look at all of our daily activities and all of the things that our matriarchs have passed along to us from a different way of looking at science. And so I hope you enjoy this video. I hope that it helps you within your class, and for all you students out there, I hope you have a deeper understanding of the knowledge that your kokums, your grandparents, your great-grandparents have passed on to you, because they're very knowledgeable in science and maths, but we just didn't know it because we didn't call it science and math. Bannock was not an indigenous North American food. Bannock is actually a survival food. So many of our First Nations, Métis, and Inuit communities, as a direct result of colonial settlement, faced famine and starvation. The government responded with providing the Indian agents ration boxes. My cuckoo Edna Clear Sky Brandon, she described the box as a 5-point box because it contained 5 ingredients: salt, baking powder, lard, sugar, and flour. So those were the ingredients that many of our ancestors would have taken into their science labs, also known as their kitchens. And over years, they would have worked with those ingredients, perfected the recipe of using those ingredients to create a product that we now know as bannock. And they would have inadvertently known, practiced, and incorporated different science, chemistry, and physics principles within their making bannock knowledge. That knowledge was passed down through oral tradition to that woman's children, her grandchildren, and through the generations to get to you or I to know how to make bannock and create this love food that we have.
Why is the bannock recipe a balance? What determines if it is out of balance? How do we know how much of each ingredient to add? How are these recipes created? A long time ago, these recipes would have been trial and error, and now each community and their family has perfected the bannock recipe that you know and love. In the Western science world, we can describe the amounts of ingredients and recipes as limiting and excess reactants. Let's break that down. Reactants are the things that get mixed together in a reaction and get used up in order to create new things. The new things are called products. In our case, our reactants are the flour, water, baking powder, etc. that gets added to your bannock recipe, and the product is the bannock itself. Limiting and excess deals with the reactants and ingredients. If there is extra ingredient left over at the end of the reaction or the baking process, that ingredient is said to be in excess. If there is too little of an ingredient that causes not all the other ingredients to be used, then that ingredient is said to be limiting. Limiting and excess complement one another. Let's continue to use bannock to help understand this. Say I'm making a bannock recipe. I add all my dry ingredients into the bowl, then I add the water, but I don't add enough. What happens? The water will start to form the dough with as much of the dry ingredients as possible, but there will be a lot of dry ingredients left over. In this case, the water is said to be the limiting reactant and the dry ingredients are the excess reactants. The limiting reactant always determines how much of the product can be made. In our example, the amount of bannock made depended on how much dough I could make, which depended on how much water I added. So the fact that your cookums know how much of each ingredient to add shows that the family or community recipe that they are using has been created with no excess or limiting reactants. Years of history and an understanding of limiting and excess reactants has created the bannock recipes that we use today. Water is an important part of the baking process. Water helps to mix the ingredients into the dough, allowing for the particles to react with one another. The water also helps unravel the gluten molecules in the process. A lot of the water will evaporate when the baking occurs, but another more interesting use of the water is to activate the baking powder in the dough. Baking powder is a combination of an acid and a base. The base is usually always baking soda, also known as sodium bicarbonate, and in the container of the baking powder that I have, the acid is monocalcium phosphate, but this can change. The names aren't super important, but knowing what acids and bases do in the dough is. Acids and bases are opposite of one another in the chemistry world. This means that when they interact, they create a neutralization reaction that balances each other out. When the water interacts with the dry ingredients, it allows the sodium bicarbonate powder and the monocalcium phosphate powder to fully interact with one another. When this acid-base reaction occurs, carbon dioxide is released.
Have you ever heard one of your grandparents, maybe a Chapan great-grandparent, say to you that you have to put your love in the bannock? Well, what they mean by putting the love in the bannock is two things. One is when we are creating food for feasts or family gatherings, we are taught that we are supposed to have balanced emotions. So what that means is that we come in a positive way to make our food for our families. The other teaching when making traditional foods is to always pray or think of the people that you are making that food for, that you think of where that food came from and are thankful for the animal that gave its life, and for the people that you are going to feed. So you think of all your family, your friends, your community when you're making bannock in that way, and that's putting the love in. And so our relatives have taught us that when we make food in a positive way, that it'll always taste lighter, fluffier, and taste the love.
Carbon dioxide is a colorless, odorless gas. You might know it as the substance that creates the bubbles and pop. People and animals also breathe out carbon dioxide when we exhale. In bannock, the carbon dioxide is released inside the dough. When the gas is released, it creates air pockets in the dough that causes the dough to rise. The neat thing about baking powder is that it will also activate again with heat. So when the bannock starts to cook, even more carbon dioxide will be released. The carbon dioxide has a hard time making its way through the dough, so it pushes the dough out of its way as it goes. That's what forms the air pockets or the holes you might see in the bannock when you're eating it. These pockets are what makes your bannock so soft and fluffy, and it's all because of acid and base reactions.
Heat transfer is often explained by the flow of energy transferred by two systems, which often flows from a high temperature to a lower temperature. In physics, temperature is a measure of the kinetic energy of the particles in a system. The higher the energy, the hotter the system. Let's visualize this concept in a larger context. Say you're in gym class. If you're standing still and not really moving around, you don't really have a lot of kinetic energy. But say you are running around and you're bumping into your classmates. This is a similar idea of what happens to particles when explaining kinetic energy and temperature. The more the particles move around and bump into each other, the more energy and heat there is in the system. So when you think about what is happening during the process of making bannock, the heat from the oven or even the oil, depending on if you're making baked bread or fry bread, is being transferred from the hot oil to the colder bannock dough, which is the work being done on the system.
What is fire? Did you know that fire is actually a chemical reaction? In fact, it's a very specific chemical reaction called a combustion reaction. All combustion reactions have the same layout. You always need a fuel source and oxygen as reactants, and it always produces carbon dioxide and water as products. Now that might seem weird. Fire produces water? In fact, it does. You just won't necessarily see it as the water will be in the gaseous form, called steam. In our case, the fuel source is the wood. Combustion reactions can use a variety of things as a fuel source, but in our case, the fuel source is the wood. Is there another source that you've noticed? How about the lighter that I used to start the fire? In that case, the fuel source was a liquid fuel called butane. Combustion reactions can be spontaneous or non-spontaneous. Spontaneous combustion reactions means that no energy has to be added in order for the fire or the combustion to occur. In our case, the combustion reaction was non-spontaneous, meaning I had to add energy, in this case another fire from the lighter, in order for our fire to occur.
With regards to cast iron pans, it really depends on how we use it. Because cast iron pans retain thermal energy relatively well, so cooking over a fire, making baked bannock in the oven, or even using a larger cast iron pan to make fried bannock would probably give best results, because the pan itself would be fully surrounded by thermal energy, which would then create an even distribution of heat to cook the bannock. According to the first law of thermodynamics with respect to cooking, the energy has to stay equal throughout the whole process. The oven's energy is being absorbed to cook the bannock, and this heat transfer changes the internal energy of both systems. Heat convection is the concept that heat is transferred by a mass motion of a fluid, such as air or water, and in this case, oil. When the fluid is heated, it moves away from the source of heat, carrying it as thermal energy, leading to a circulation in the liquid, like heating oil for the fried bannock, or even heat created by the oven for baked bannock. So, convection is this idea that the cooled, more packed fluid near the surface moves downward, and the patterns of circulation can be formed. Warmer particles from the bottom move to the top, and the cooler particles at the top move to the bottom. Convection above a hot surface occurs because hot air expands, which means that the particles are not as closely packed together, but they also rise, creating a sort of circular motion of the moving particles. With regards to making bannock, the air pockets created by the baking soda in the bannock interact and expand with the uncooked dough to create a fluffier consistency instead of having a dense, hard bannock. While poking holes in the bannock's dough help the bannock cook more evenly. The convection heat created by the oven or the oil allows us to cook the bannock, and with respect to the thickness of the crust, we have to think about the time in which we cook the bannock. The longer the outer area of the bannock is being exposed to heat, the more it is being cooked. By creating those holes, we can lessen the time of cooking the crust to ensure heat and energy is reaching the middle of the dough and not burning the outer edges.
The other teaching that comes with making bannock is you can see my hands. I'm not quite old enough yet, but they're starting. If you can see my hands here, the fingers are starting to curve in and they're separated. This is why, and this is the teaching that was given to me by my relatives, was there's a reason why we slice our bannock in that certain way. It's supposed to look like granny fingers. It is to remind us that as we get older, we will think and put more love into our food. It always reminds us of our elders and the ones that pass along all of these recipes and all of the teachings that you have learned through your matriarchal family structure. That's why we cut our bannock in those strips, because it's to look like granny fingers, because it reminds us of our teachings, where they come from, and who holds that knowledge, and it reminds us to take care of them. and that they are just as fragile as a piece of dough. That's how it was explained to me, and I hope that that teaching passes along to you in a good way. Thank you for watching our Chemistry and Physics of Bannock video. This video was made for our students so that you can use this in your classroom and also be able to teach your caregivers, your children, and your friends about the science behind Bannock. The Canadian Light Source education staff are custodians of traditional knowledge and traditional cultural expression, where our main goal is to empower our students with scientific resources to make culturally appropriate decisions of how their CLS experience will contribute to their future generations and improve Indigenous communities. As custodians of this knowledge, the CLS Education has developed some standards of behavior and protocols. So one of those is that this video was produced for the intended purpose of creating a STEM resource for Indigenous students and teachers who are incorporating traditional knowledge into Western science. And we would ask that you would contact the CLSI creators if you intend to use this video for any other purpose. Thank you.